as it relates to the golden ratio, phi, and the Fibonacci sequence.
Firstly, I would like you to look through these rectangles and pick one rectangle that most embodies rectangleness to you. Is it A, B, C, D, E, or F? What do you imagine when you think of a rectangle? If you picked B, then you are like most students in my math class. Theoretically speaking, people are 8 times more likely to choose this rectangle over the other given rectangles. The natural ratios behind the side lengths psychologically appeal to the brain.
That is why this rectangle is taught to be the rectangle to younger students. This rectangle is not only aesthetically pleasing, but also features unique deductive qualities. A few months ago, my math teacher challenged me to delve deeper into these features of the golden rectangle, one of geometry's most notable phenomenons.
In researching, I learned that the ratios of the golden rectangle's side lengths were a ratio of 1 to 1 plus square root of 5 over 2, or 1 to Greek letter phi. I came across the diagram below as well, which demonstrated yet another enticing feature of the golden rectangle. The rectangle, with sides A and B, placed adjacent to a square with the same side length as A, produced a larger golden rectangle with sides A and A plus B. This newly formed rectangle was similar. Similarity is when a figure maintains the same angles and all the sides are multiplied by the same scale factor. This can be proven with a little bit of algebra. Firstly, let's take a look at the golden rectangle, with sides A plus B and A. Using phi, we can prove that the two rectangles are indeed similar. Let's start off by giving A and B numeric values, making them variables. I will assign B 2. You can assign B any numeric value. Hence, in this case, A equals B times phi. Using systems of equations, we can conclude that A equals 2 times phi, so A equals 2 phi. Now let's plug this in for a rectangle and square. The rectangle's dimensions are A times B, thus the numeric dimensions would be 2 times 2 phi. The square's dimensions would be A squared, or 8 times A, thus the numeric dimensions would be 2 phi times 2 phi, or 4 phi squared. The new rectangle's dimensions are A times A plus B. Based on our previous conclusions, the numeric value would be 2 phi times 2 phi plus 2. After plugging in phi's approximate value, which is 1.618, we can conclude that the large rectangle is similar to the smaller rectangle, as there is the same ratio. Thus, when adding or removing a square from the golden rectangle, another similar golden rectangle is formed, maintaining the side length ratios of 1 to phi. Pretty impressive, right? This logarithmic spiral continues to follow the golden ratio. Now you may be wondering, how do I construct a golden rectangle? Firstly, you may create a rectangle using the side length ratio of 1 to phi, or create a scaled version of the diagram previously demonstrated, with side lengths A plus B and A. However, using the Pythagorean theorem, where a squared plus b squared equals c squared, and any right triangle, we can construct a circle meeting the outmost point of the golden rectangle, with a radius which is the diagonal to half the square in the golden rectangle. From here, we notice that the golden ratio is still prevalent. There is a special relationship between the golden ratio and the Fibonacci sequence as well. The Fibonacci sequence is a sequence in which one term is the sum of the preceding two terms in the sequence. The first 10 terms of the sequence are 0, 1, 1, 2, 3, 5, 8, 13, 21, and 34. Algebraically, this is denoted as x sub n equals x sub n minus 1 plus x sub n minus 2, where n is the number in the sequence and is greater than 1, and f0 equals 0 and f1 equals 1. For more information on the Fibonacci sequence, visit mathisfun.com. When dividing the second term with the first term, or the fifth term with the fourth term, or the ninth term with the eighth term, and so on, we get a resulting quotient that is very close to phi. As the terms get larger, the quotients get closer and closer to phi, but never quite reach the infinite number of phi. This idea can be applied to the golden rectangle, as the side lengths of the golden rectangle maintain the ratio of 1 to phi. Looking into this spiral, we can see that the areas of the figures are the same as the Fibonacci sequence. We can see the sequence and ratio appear in nature as well, in organic form. We can recognize it in the nautilus shell below. As you can see, the distance between the ridges follows the Fibonacci sequence and golden ratio. This is also prevalent in many flowers, especially the arrangement of sunflower seeds. Additionally, spiral growing plants also generally follow the Fibonacci sequence and golden ratio. We can see the sequence in pine cones as well. Just flip over a pine cone and count the ridges. Architects also use the golden ratio when constructing and designing various staircases and buildings. Even the Parthenon in Greece features the golden rectangle.
The next time when you go out for a walk, pick up a pine cone and count the ridges. See if you can identify the Fibonacci sequence. If you enjoyed this video, please like, subscribe, share, and turn on your notification bell to get notified every time I post a new video. Thank you!
I would also like to give a special shout out to my math teacher, Mr. Plott, who inspired me to make this video. This video was created with the aid of PicCollage and iMovie. Here is my works cited page.